Okay, so it's really important to establish this issue that the area under the curve of the derivative is equivalent to the displacement of the antiderivative or the original function. So if I take the sum of all the areas, so the velocity times changes in time, if I sum all those up, I'm going to get this total area underneath the graph. And that total area is equivalent to the net change in position of the original function or the antiderivative function. So the derivative of d gives us v, the v times the width, the dt, or the width of the rectangles, summing those all up gives us area. And this is the same as taking the displacement from A to B. Okay, so net area from x equals A to x equals B. This gives us a net displacement from A to B. Okay, so this little line here is notation actually, and it just allows us to keep track of those bounds. Okay, so if we take a look at a t-squared graph, okay, the original d graph, well, it had to be cubed, okay, but cubed is going to give us 3t cubed, so I need to account for that. I'm just going to divide by 3, and we don't know of this c value. Okay, so we don't know that there could have been a constant which differentiated to 0, so we don't know. Okay, so we're going to put a plus c there because there could have been a constant there that we had to account for. Okay, so that's our derivative function. So that is our original function that differentiates to t squared. Okay, so t cubed over 3, we'll call that plus c. Just checking this. This is going to give us 1/3 times 3, which cancels out, and then power 2. Yeah, that's our derivative function. Now, if I were to think of this function, and I want to know how far they moved when the time was 0 to time was 10. Well, we don't know where they start. That plus c kind of tells us where they start. But when we talk about displacement, it doesn't really matter where they start. We just want to know the difference. So I want to do d at 10 seconds. And then we're going to take that and we're going to find, I'm just going to write it this way. The change in d is equal to the d at 10 seconds minus the d at 0 seconds. Okay, well the d at 10 seconds was 1,000 over 3. And again, that plus c is a bit of a bother. It's a bit of a problem, but I want you to notice that, oh, that plus c actually, when we talk about displacement, it doesn't matter. Those plus c's cancel out anyways. So we get a net displacement of 333.3 meters of displacement. Okay, and if we take a look at the area underneath that curve, it's kind of hard to tell, but from 0 to 10, okay, well, that's going to be, that's going to be 100 meters per second. Yeah, that's going to be 1,000. That area is 1,000. That rectangle, I'm just going to highlight this rectangle. This rectangular area, that's going to be 1,000 meters of area. And the area underneath that curve, yeah, that is reasonable to say that's about 1/3 of that area. Okay, yeah, so that's going to be about 333.3 meters of displacement. That's a reasonable result. Okay, let's take a look at cosine. Well, if we know the derivative of sine is cosine, so that must be our antiderivative function. Okay, so I'm going to write that as d of t equals sine of t. Well, again, there's that plus c that could have differentiated to 0 that was originally there before we differentiated. But as we saw before, it's maybe not so much of a problem. So taking a look at our cosine function, this cosine looks like that. Okay, so from 0 to pi over 2, that should be my displacement right there. Okay, that should be the distance or displacement that I travel. Well, if I want to calculate that area, I can't really calculate that using rectangles. Same with here. Rectangles don't really do it justice. But if I really believe that the displacement is related to the area underneath this curve, I could use this function to find the displacement instead of using a whole bunch of little rectangles. Well, let's try it again. So that area, that's going to be about 1.57, right, pi over 2. And that's going to be 1. So that looks like, that's about 1.57. And that looks, I'd say that's about 2/3, or let's say close to 1. Okay, that's not really a great picture either, but let's say that's close to 1. That would be a reasonable result. So if I want to find out the displacement here, the change in D should be the area underneath this curve. That's a reasonable, that's the premise that we're working on. That's what we're trying to establish, and that's what we're saying is true. Okay, so we're going to say that sine at pi over 2 plus c minus sine of 0 plus c. Well, conveniently the plus c's cancel out. Sine of pi is 1. Sine of 0 is 0. So we're saying that the area is 1 square unit. Yeah, that's not so far off. If I actually drew this a little bit better, okay, so sine function looks more like, or cos function looks more like that. It's a little bit better, right? Yeah, that area represents about 2/3 of that rectangle. And we know that rectangle is about 1.57 because the height is 1, the width is 1.57. That's reasonable. Okay, well, let's take this one more step. I want to go from here, to pi over 2. Sorry, 2 pi. I want to go all the way to 2 pi. Well, the net displacement should be the total area. Well, I went forwards here. I'm going to go backwards and forwards. Well, it's looking to me that I've gone forwards the same amount as I've gone backwards. And if I calculate the net displacement, is that really going to be true? Let's check. So the net displacement should be from sine of 2 pi plus c. Okay, and then we're going to take from pi to 2 pi. Oh, sorry, I've done that differently. So let's take that. Let's actually do from 0 to pi to start. Okay, so this is going to be from 0 to 2 pi. And then we'll do the part B after. So this is sine of 0 plus c. That's going to be 0 minus 0, which is giving us a net displacement of 0, which kind of looks correct, right? From start to finish, our net displacement looks like it's 0. Okay, so let's do part B down here. Part B was from pi to 2 pi. Okay, so from here, pi to 2 pi. So that looks to be the same. It looks like from here to here, the net displacement should be again 0. So the change in D is going to be sine of 2 pi. I'm just going to leave out this plus c from now. We don't need it. Sine of 2 pi minus sine of pi. And again, our net displacement is 0 because we have the antiderivative positions were 0 and 0. So it seems to confirm that the area underneath this curve is related to the displacement on the antiderivative, which would be the sine function in this particular case. And that is a central idea. That is a big idea in this unit.